In this video, I want to look at how we can use symmetry to discover some important facts about definite integrals. I want to start with the integral between minus pi and pi of, let's make it the sine of x dx. Now what I want to do is I actually want to start by drawing a picture. So let's see, let's draw an y-axis and an x-axis like this. And what I want to do is I want to know that I know what y equals the sine of x looks like. It happens to be symmetric with respect to the origin. In other words, I know that this chunk here and this chunk here are exactly the same because the sine of x is an odd function. So y equals sine of x is odd, and hence it's symmetric about the origin. And what that means is that if I have a point a comma b over here on the curve, I also have the point minus a minus b over here. And so these two chunks of area are exactly the same size. So as area, A1 and A2 are exactly the same as just ordinary old area, so as plane areas. And that's because of the symmetry of the sine function. Well, when I look at this definite integral, this particular definite integral is, of course, the area above the x-axis subtract off the area below the x-axis. And so this would be A1 minus A2, which is a big fat 0. Now, the reason this works is that we're looking at going all the way out to pi comma 0 on this side, and we're going back out to minus pi comma 0 over here. In other words, the two endpoints on my integral are symmetric with respect to each other. There's nothing particularly significant about using the sine of x here. Any odd function is going to behave the same way. So let's kind of look at the general case of odd functions. So if I let y equal f of x be any odd function, then it turns out that the integral from minus a to positive a of f of x dx is always going to be a big fat 0. And the reason why is similar. And so I'm just going to kind of draw a schematic picture of how this would look. If I have an odd function, what I know is that the graph is symmetric with respect to the origin. So y equals f of x is symmetric with respect to the point 0, 0. So what that means is that it's going to have to go through 0, 0, and if I come up like this and then go down, I'm going to have the same kind of an idea over here, but a mirror image. It's going to go down and then come back up, and this is not looking very good because I have a hard time drawing these things sometimes. So let me get this picture drawn a little bit better. So let's see. I'm going to be going like this. And this stuff here is symmetric with this stuff over here. So in particular, this chunk here that I'm going to call A1 and A2 are going to cancel each other out. And if I call this A3 and this chunk A4, A3 and A4 will cancel each other out. So any kind of an odd function is going to have the fact that if I go from minus a to positive a of f of x dx, the net area, the signed area, is going to be a big fat 0. Well, let's just do one basic kind of an example before looking at another related fact. Y equals x cubed is an odd function. If I look at the graph of this, well, let's see, let me clean this up and make a better graph over here. I'm actually going to draw the graph first. This graph looks like this. And the, oops, boy, that axis is not a good axis. Let me make the axes with my line tools. So one axis would be here, the other axis, oops, would look like this. And everything is symmetric. So what's going on here is that if I go from, say, minus 10 to positive 10, and I want to look at the definite integral between minus 10 and positive 10 of x cubed dx, that's going to be a big fat 0 because these two chunks of area will be symmetric and they will cancel each other out. Okay, well, let's look at even functions now. So, what about even functions? So let me think in terms of something like the integral of, let's make this one go from minus 4 to positive 4 of just x squared dx. Well, this is going to be a nice fat parabola. And here again, my axes are not very good, so let me try and draw axes that are, yeah, that axis is also not very good. So let me try and draw the axes first. So, oops. So there, now I've got some axes. And this would just be a nice parabola, like so, going through 0, 0, and minus 4 over here and 4 over here. And what I want to notice is that this particular area here and this particular area here, again, are the same. And so what this is going to wind up being is it will be twice the integral between 0 and 4 of x squared dx. Now, we have not yet learned how to figure out this particular area, but it's important to note that all even functions are going to behave in this same kind of fashion. In other words, if y is equal to f of x is an even function, then the integral between minus a and a of f of x dx is always going to be equal to twice the integral between 0 and a of f of x dx. And the basic reason why is symmetry. In other words, an even function is always going to have the property that it is symmetric across the y-axis. So no matter what the function does over here, it has to do the same thing over here. And so if I'm going from minus a to a, this chunk here will equal this chunk here. And so the integral from minus a to a will simply be twice what we have on this particular side of the y-axis.